Okay, this video is going to go over specifically chemical equilibria. Now, I'm going to tell you up front that the homework assignment involves some of the videos that are actually in the slideshow. So you're going to want to make sure that you stick with actually going through the slideshow and watching the videos that are in it. So the very first questions are related to this demonstration video. I think just like the escalator video in the last one, it's an important video to help you understand what equilibrium is and kind of what it looks like. It gives you a visual demonstration, even though you can't see a chemical reaction happening. It does mostly deal with what looks like quantities of reactant and product. And we're going to talk a little bit about more difficult ideas that have to do with parts of a reaction you can't see. Now, I'm going to reiterate that there was a pattern through all of our conversations about equilibrium, and that is that equilibrium is not about quantity being equal, it is about the rate of two processes being equal. One process moving in one direction and the other process going in the opposite direction, sort of undoing what the first process was doing at the exact same speed. That does not mean that there is no movement or no energy involved. It means that there's actually constant motion. And that constant motion is creating a situation that allows that equilibrium to be maintained. And that constant motion is known as it being dynamic. So it is constantly adjusting to preserve the equilibrium. Okay. When a reaction has reached equilibrium, just like in a physical equilibria, it will look like things are standing still because every time a motion gets done, its opposite occurs. So this is a little bit like if you can imagine I was knitting a sweater. If you've ever pulled a sweater and like had a yarn piece of yarn come loose and then just started pulling it, the sweater will unravel and it will become unknit basically if you don't stop pulling on the yarn. So this is a little bit like if I were knitting a sweater and somebody was pulling the other end of the yarn and unknitting my sweater as I was knitting. As long as they were doing it at the exact same speed I was doing it, it would look like I never knit a sweater, but I would be constantly knitting and the other person would be constantly pulling. Okay, so the situation is that the amount of reactants and products, or the concentration of the reactants and products, is going to look like it is remaining constant. And essentially, it is staying constant because as long as it's at equilibrium, for every reactant that becomes the product, some of the product will break down into the reactant. So let's talk about that some more. So once an equilibrium is established, and at the beginning of the demo video, you'll see that the equilibrium hasn't happened yet in the beginning. And then the teacher is going to start asking kids questions about when are you there? When are you at the equilibrium? Okay. But once an equilibrium has been reached, um, it is constantly working at maintaining itself. But if you make a change to that system, we call that applying stress to the equilibrium. In other words, we do something to try to mess it up almost. And then the equilibrium will work to try and undo whatever we did. So there is some amount of stress that an equilibrium can handle. But at some point, it will stop being at equilibrium if you push that level of stress too far. So I've never seen them ask a question about this, but since we're talking about the topic, we should do the whole topic. So just quickly to make sure our butt is covered in case they do throw some weird questions on the Regents this June, we should talk about what breaks an equilibrium. So if you've got a phase equilibrium, like a liquid and a solid, like ice in water, what will break a two-phase equilibria is if one of the phases completely disappears, right? So once all the ice is completely melted and you only have liquid water, equilibrium over. Same thing with a phase equilibrium between a liquid and a gas. For example, if you were to take the cork out of the bottle and all the gas were to go out of the bottle, you would lose your two-state equilibria. You wouldn't have both states present because the gas would be able to leave. If it's a solution equilibrium, you can really only break your equilibrium if something is done to make it so that your solution is no longer saturated. Like if you added extra water and now your solubility has changed, or if you change the temperature and now you could dissolve more solute, um, or if you, yeah, that's pretty much the two things that would break that equilibrium. If you added more water, and that would make your solution not saturated anymore. Or if you change the temperature, particularly if you raise the temperature. Because if you raise the temperature, usually if it's a temperature dependent solubility, you would be able to dissolve more because you made the temperature higher. So the last one is the chemical equilibrium. How do you break a chemical equilibrium? You would have to run out of one of your reactants or your products. So when you're messing with it, you can mess with it to a point, and then at some point you can go too far and you'll lose your equilibrium. Um, and then you'll only have one process happening in one direction and it'll be over. Okay, but we're going to work with the idea that we have a working equilibrium, an equilibrium that's currently dynamic, meaning it's constantly shifting to maintain itself. And it is also going to respond to stress that way. And we're going to try and stay within the boundaries of that equilibrium happening. So, one example I could give you for a system shifting to compensate would be if I were carbonating soda. So, the soda I chose was Sprite, most likely because that's the soda I drink. I don't drink soda really, but if I do, I drink Sprite or ginger ale. Just, because I'm sure you really cared. So carbon dioxide is the gas that gets dissolved into soda to make it bubbly. And carbon dioxide, being a gas, doesn't really like to be dissolved in a solution. As you know, gas particles really don't have very strong forces of attraction. They don't really want to be near each other. They certainly don't really want to be with water molecules. So, how do you force that situation to happen? You push the gas in by applying tremendous amounts of pressure. That means that this is an equilibrium that has to do with gas, so pressure is a factor. And um, if you were to have this in a sealed container, like when you have a closed bottle of soda, there is an equilibrium that has occurred, and you're able to keep the gas, a certain amount of the gas, in the liquid. Okay, now this is what that equilibrium would look like. Now, keep in mind, this is basically a solution. You're dissolving carbon dioxide in water. You're forcing it to dissolve in water, but it is a solution equilibrium. It's not a phase equilibria, and it's not a chemical reaction. Okay, so you've got carbon dioxide as a gas in equilibrium with carbon dioxide dissolved in water, which is aqueous. Okay, so if you wanted the equilibrium to favor more carbon dioxide dissolving in the solution, now you have to think about how would you manipulate the system to favor more carbon dioxide wanting to go into solution. So when you're doing the slideshow, you're going to watch this other YouTube video, and that will give you some background also about this. It's actually, this is kind of like a bonus video if you want to see the manufacturing process and how they carbonate soda. Um, if you could guess, I think you would have to push this piston down, right? So see that there's a red arrow at the top of the piston. If you pushed that down and applied more pressure, you could force more carbon dioxide to go into the water. So in this case, this equilibrium would be impacted by pressure. Okay. Um, Now, this is two different scenarios. So on the left, I have carbon dioxide, and the container is more open, right? So I have less pressure in the container on the left. On the right, I have increased pressure, high pressure. See, it says high pressure at the top. And at that point, you can see more blue dots representing the carbon dioxide have been forced into the solution. So this is an example of changing an equilibrium by applying the stress to it by literally putting pressure on it. Okay, so the system in this case will favor more carbon dioxide going into the solution because you increase the pressure. All right, now Henri Louis Le Chatlier, so it said Le Chatelier's principle because it's French. That's how they pronounce it when it's IER at the end. Was a French engineer, and he came up with this principle. So the basic idea is that if you stress an equilibrium, you disturb it, it will adjust in a way that will minimize change and try and get back to a point of equilibrium. So this is known as shifting, and it means shifting in the direction of one process or the other. So in this case, you stress the equilibrium by applying pressure. So it shifted to the right. Let me just show you what I mean by to the right. So you've got two arrows here, right? Correct? One is going to the left towards carbon dioxide wanting to be a gas. And the other one's going to the right towards carbon dioxide wanting to be dissolved in the solution. Which side of this process, which the back, this we call this the reverse process and this the forward process. Which process is going to be favored if I apply pressure? Well, the forward process will be favored. If oh, that's actually how you write a force vector in physics. Ignore me. Okay, if I were to raise the piston, I would lower the stress, and so the equilibrium would shift in the reverse direction and favor carbon dioxide being a gas and not being dissolved in solution. So this is an example of it when it's a physical equilibrium. We're now going to move forward and start talking about chemical reactions and how you stress a chemical reaction. So there's three major types of stress. The first type of stress is that you either add more reactant, you can actually add more product, like an already made version of the chemical, or you could find a way to remove some of the reactant or remove some of the product. That's one way that you could stress the reaction and force it to shift either in the backwards direction or the forwards direction. Now, number two, you could also change the temperature. If temperature impacts your reaction, right, say it's endothermic or exothermic, you could, again, force the reaction to either go forward or go backwards. You could change the pressure. Now, there is a caveat here, and we mentioned it several times. Changing the pressure only impacts reactions that have gases involved in them. More specifically, in most cases, you have to have 100% of all the reactants and products are probably going to be gases in that reaction. Some of the most famous one being the Haber-Bosch process, which we talked about in the last slideshow. So remember that pressure doesn't impact equilibriums that don't involve gases. So just watch out for that because number three only affects reactions involving gas. So that to me seems like the kind of thing they're going to put in a question that's a trap, right? It's a trick. They're trying to get you to pick something that isn't possible in that scenario. All right. So when you are changing the amount of reactants and products, that will basically always affect every equilibrium. Changing temperature will primarily affect endothermic and exothermic reactions. A large number of reactions are sped up by heating them up. If you remember, one of our safety steps is that if you're rinsing your hands off because you got chemicals on your hands, I told you to use cold water. And that's because a lot of chemical reactions are sped up by the addition of kinetic energy from hot water molecules. So you want to use cold water to take energy away from that reaction and slow it down. This is also, there's like a lot of really weird household tricks, but also just everyday things that you do that you don't realize why you do them. They have to do with removing energy from possible chemical reactions. So there is like I don't know if you've ever heard this. Some people put their batteries in the refrigerator to make them last longer. That is because batteries are run, they contain chemicals inside them that have a chemical reaction that are making electricity. If you slow that chemical reaction down by putting them in the refrigerator and taking kinetic energy away from the particles in the chemicals, you will make the batteries last longer by slowing down the chemical reaction in the battery. The other thing you do just routinely is you put food in the refrigerator. The reason why putting food in the refrigerator keeps it from going bad is that you are trying to slow down a number of different chemical reactions. The first type of chemical reaction you're slowing down is the chemical reactions that living organisms like bacteria are going to do while eating your food. Okay, if they're able to eat your food and digest it, they will multiply, and then all that extra bacteria in your food will get you sick. So, if you can slow down their digestive processes, their chemical metabolism, you can slow down how fast they multiply and keep your food safer and keep it from spoiling. The second one would be that there are other chemical reactions that happen that make food spoil. Oxygen reacts with things in your food to oxidize it and make it go rancid, like oxidizing oil makes your oil go rancid. And there are, stray atoms in there that might be a little extra reactive, like metals, little metal atoms, nothing that will hurt you necessarily, but those atoms can react with the atoms of the molecules that make up your food and make your food spoil faster. And so refrigeration slows the spoiling of food down and preserves it. That's 100% a chemical process. The opposite of that would be cooking your food. So when we cook food, that's a chemical reaction too. And you make that reaction happen more quickly by applying heat. Okay, so um, that's like everyday stuff that you actually do. Changing temperature, affecting reactions, chemical reactions, by slowing them down or speeding them up. So again, changing pressure will only affect gaseous reactions. So I included a video here. You're going to need to make sure you go and actually watch that video. Um, we're going to back up because I didn't click that link. To make sure that you get the full rundown on the Haber-Bosch process. Oh man, sorry you guys, I made us lose our place. I did not mean to click on that. I'm on my laptop, my home laptop, and it's a lot more sensitive. Okay, I have a touch screen, so I touched the screen and accidentally started it. Okay, so what do I mean by shift? So again, you see your two arrows. Backwards means that the reverse process is happening and undoing whatever is the process is. And forward means you're going to, we often say left and right because we write this on paper and we read it from left to right. So going to the left is the reverse reaction, going to the right is the forward reaction. Okay, so forward reaction is usually making the thing, making your product, and your reverse reaction is taking your product apart and making it back into reactants. So shifting refers to a change that causes the reaction to either go forward and make more product or go backwards and make more reactants. Take product apart is going backwards. Okay, so when you do a shift because the equilibrium is stressed, those are your only two options. Either you can make more product and go forward, or you can take product apart and make reactants. That's it. You can't do any other side thing. Those are the rules, right? So this reaction was already doing its thing. It's either going to go backwards or forwards. That's all it can do. It's a two-way street. It only does that. Okay. So this is kind of how this progresses. You have a happy equilibrium. It's doing its thing. It's in constant dynamic motion in order to maintain itself. And that means that it is doing something, it is reacting, but the forward reaction is getting undone at the exact same speed by the reverse reaction. And so your concentrations are going to look like they're constant. Then something is going to be changed. Okay, that equilibrium will then be forced to revert. Sorry, you guys, I keep hitting things. Yes. Okay. And then the concentrations of your reactants and your products might actually change. So the concentrations can change in an equilibrium system. They're not going to stay constant if you're stressing the equilibrium. If a question says the system is at equilibrium, the concentrations are going to stay constant. But when you're applying Le Chatelier's principle, you are assuming that you are messing with this equilibrium. Okay, so you are in a period of it having to adjust. Once it gets back to its happy equilibrium, then the concentrations will become constant again, but they may not be what they were before you stressed it out. Okay, so a new equilibrium will form after it's stressed. And at that point, the rate of the forward reaction and the reverse reaction will be constant again. Okay, so what are the stresses? The change in concentration of the reactant of product. If you're dealing with pressure reactions, gaseous reactions, you could be squishing it by changing the volume of the container, or making the container larger that would relieve pressure. Again, only affects reactions that have gases, or you could be heating it up or cooling it down. That means you're either inputting heat or taking heat out. And again, unless that reaction says that it's endothermic or exothermic, it shouldn't really impact it. Okay, so when you are talking about how will this impact your reactant or your product, this is an equilibrium, you are currently stressing it out. Okay, if one change is made to a chemical species, the equilibrium will shift so that that species recovers. Okay, species is just a fancy way. I was thinking about this today while I was walking down the stairs on my way into school about how we keep changing the science vocabulary on you. I'm so sorry, you guys. I wish people would just get their vocabulary straight at the sciences, right? In biology, when we say species, we mean like, what kind of tiger is that? And in chemistry, when we say species, we mean what kind of reactant or product is that? Um, but there are many other words in biology that mean totally different things in chemistry, right? So everybody else in a reaction changes just to help that one species stay the same. So it's kind of a weird situation. The one you mess with will get to go back to what it was doing, but everyone else will have to change what they're doing to fix that one. Okay. So for example, here is an equilibrium between sodium dioxide. Sorry. Oh my gosh, you guys, I just did what a whole bunch of you do. Sulfur. That's sulfur, not sodium. You could tell how sleep deprived I am. All right. Sulfur dioxide. Whew. Should I go in and edit that back out? No, I think you're just going to have to deal with it. Grace can make fun of me later for it. All right, is reacting with oxygen gas, that's a diatomic gas, to give you 2 moles of sulfur trioxide. If I were to increase the amount of SO2, all right, so let's talk about the different ways that this can be messed with, right? So here's my reactants. They keep saying that, but this is what I'm talking about. Here's my ingredients, right? Here is my product. An equilibrium is a very different situation than most chemical reactions. In a one-way reaction where you only have an arrow going in one direction, when the reaction's over, all you have left is products. In an equilibrium reaction, the reactants and the products are actually both present at the same time, because if they weren't both there, the equilibrium would be broken, right? You have to have the reverse process and the forward process happening at the exact same time. And so therefore both things have to be present, right? So if I were to increase my amount of reactant, this is the person I'm messing with. So this is the person who's going to try to adjust. So the reaction's going to shift to try and make it so SO2 stays the same. So if you have too much, it's going to try and get rid of the excess. How do you get rid of excess SO2? If your only options are either to make SO3, the forward reaction, or take SO3 apart and make SO2. Well, I already have too much SO2. I added more. So the reaction's going to be like, oh, quick, get rid of this. We don't want it. Try and get it back to the same amount of SO2 that was already there. It will break this into pieces it will, if it's, it will break this into pieces or it will make more SO3. So it will favor the forward reaction. Okay, so SO2 will react with more oxygen to make more SO3 to get rid of the extra SO2. So as long as you have enough oxygen for this to react with to let the reaction shift forward, you should be fine, and the equilibrium will recover. So it's important that you really understand what's happening and what your options are when you do this. There are some tricks that people teach to try and remember, like by drawing arrows and stuff. I think that's kind of not really the goal here. The goal is not for you to memorize a trick. The goal is for you to understand what's happening. If you then come up with a trick that helps you remember what you understood, that's fine. But you should definitely make sure you understand what's happening. Okay, so again, I've got a forward reaction and a reverse reaction. I'm going to go red again. My forward reaction goes this way and makes more sulfur trioxide. My reverse reaction goes backwards and makes sulfur dioxide and oxygen. So if I do something to this side, so say I increase this one, or I increase the oxygen, if I increase this, the reaction will shift to try and get rid of the extra that I added. Okay, that will force the reaction to go forward and make more product. So the concentration of this will go up. The concentration of this, whichever one you changed, will stay the same. Okay, so let me see if I have some practice questions for us to do. You will, because you have homework after this. All right, so I made you a little table to help you know what's going to happen. You know, I just thought about this. I should probably talk about, I should have added to this table whether the reaction goes forward or backwards. So if you take some reactant away, the reactant will increase. So the reaction will try to replace what was taken away, and the product will decrease because the only way for you to get more reactant is to take the product apart. If you add more reactant, the reaction will shift forward. All right, so how about this? I'll write it while I'm saying it. So reactants removed just realized. Oh, okay. I don't know if my annotation bar gets in your way, but if reactants are removed, the reaction will shift backwards to replace what you tried to break. And the only way for it to replace reactants is to break products into pieces again. And so the reaction will go in reverse. The reactants will go back to what they were doing. They'll kind of stay constant, and the product will go down. Okay. If you add more reactant, oh, I see how I have this table set up. I think I need to redo this table. It's too confusing. All right, here's what we need to talk about. I may have meant it for this specific reaction. So let's talk about it for this specific reaction. SO2 plus O2 reacts forward or backwards to make SO3, right? So I'm not going to balance it. I want to just talk about in general. So if I remove some of this reactant is what this table means, right? I will have to take this apart to replace it. So the reaction will go backwards. That means that my oxygen will increase because I'll have extra oxygen from taking this apart. This will go back to what it was doing. That's my whole goal, right? To fix the equilibrium, I try and get whoever was bothered to go back to what they were doing before. So that will actually stay constant. And this will actually have to be decreased because I have to use it up. I have to break it into pieces to replace what you took away. Okay. So if you think about it with that specific reaction in mind, that's why this table needs to be interpreted. Okay, so here, I have it kind of broken down for you. I add SO2. If I want to get rid of the excess SO2 and get SO2 back to what it was doing before, I have to go forward and use it up. So that means that my oxygen is going to go down, my SO3 is going to go up. Okay, so this is a change that would cause the reaction to shift forward. Here's our Haber-Bosch process. The formation of ammonia is favored by a couple of different things, right? So we have to first know what ammonia is. Ammonia is the common name for nitrogen trihydride, which is written like that. So this is my ammonia. Now, if I was reading this question on a test by myself and I didn't know what ammonia is, how would I know which of these chemicals was ammonia? Well, a couple of different things. First, you should know nitrogen and hydrogen. They're elements. They're diatomic elements. You should know them. So by process of elimination, the only person in this equation that you don't know is the person who's ammonia because you know these guys are not ammonia. Let's talk about it another way. Let's talk about language based. The word produced implies that that's the product of the reaction. The product of the reaction is the one on the right-hand side after the yields arrow. So this is the product of the reaction, so NH3 is ammonia. Okay, we have some processing issues here with some people who want to make sure you really understand how to process this fully and make sure you know what we're talking about. All right, let's go back to talking about shifting some things. If I want to favor means I want that to happen, right? I want to favor ammonia forming. What can I do to this reaction to make it go towards making more ammonia? That's the forward reaction. Well, first thing I could do is I could add more N2. That would favor the forward reaction. I could also add more H2. That would favor the forward reaction. Those are pretty much my two options. Another thing I could do, if I wanted to go forward and make more ammonia, I could take some ammonia away. If I took ammonia away, some of my product away, the reaction would be like, hey, what are you doing? And it would try to fix the equilibrium by replacing it. So that would force the reaction forward. Now, this is an exothermic reaction. So this gives us an opportunity to talk about this whole heat thing. The trick to this is to think of heat as either a reactant or a product. You're either putting it in like all the other ingredients, or you're taking it out like a product. Okay, so once you get the hang of figuring out if you should add product or reactant or take reactant or product out to make a reaction shift, that will tell you basically what you need to do with the heat also. So I just said if you increase the N2, that will make the reaction go forward. If you increase the H2, that will make the reaction go forward. If I take away NH3, the reaction will shift forward to try and replace what I took. That means that this same thing applies to heat. If I treat heat like a product, okay, you might want to pause that and rewind it. It's an important point. If I take NH3 away, the reaction will be like annoyed and it will try to move forward to replace it. That's how it's going to try to reestablish the equilibrium. That's what Le Chatelier's principle says it will do. Okay. If I treat heat like a product, that would mean if I want the reaction to go forward, I have to take heat away. That would mean I'd have to lower the temperature. So the same thing applies to both of these, right? So getting this reaction to happen at a lower temperature, manipulating, this is also a gaseous reaction. So we could also talk about, let's talk about pressure last. All right, so we talked about reactants and products. We talked about temperature. Now let's talk about, this is a gaseous reaction. That means it's impacted by pressure. So this is where the stoichiometry comes in. Don't worry, it's not math. Don't worry, it's not math. All you have to do is be able to read the coefficients. Okay. On this side of the reaction, I have, that was supposed to be a 1. It was terrible. 1 mole of nitrogen and 3 moles of hydrogen. So that would mean that on the reactant side of this, I've got 4 moles of gas. Okay, a mole of gas takes up 22.4 liters of space. So if you can imagine a soda bottle is only 2 liters and every mole of gas that you have takes up 22 liters, it's quite a bit of space. Okay, so if you've got 4 moles, you've got 80, oh geez, yeah, 88 liters of space that you need to have 4 moles of gas there. Okay, if you to go forward though, this side of the reaction only has 2 moles of ammonia gas. When they recombine, they take up less space. So this takes up less room. So this takes up a lot of space. This takes up about 88 liters of space. So let's write that down because this is important. 22.4 liters of volume is the amount of space that 1 mole of gas occupies. So if you can make ammonia, it will take up less space. So in this case, it will only take up about 44 liters of space. So if you just think about it that way, right? If I squish this gas, if I put it under pressure, it will have less room. And so the reaction will actually shift in the direction of taking up less space. And so if I want this reaction to shift forward, I have to increase the pressure. But if I want it to shift backwards, I would decrease the pressure. And that would be like, oh, okay, well, we could go back to making 4 moles of gas because we have more room. So that favors the reverse reaction if you decrease the pressure. Okay, so that's actually all 4 factors in one reaction. That's why everybody likes to talk about the Haber-Bosch process. Okay, so increasing the hydrogen or increasing the nitrogen is one option. There's actually 4 different options. We just went through all 4 of them. Let me back up one sec. Do you want me to, let me write out all the different options so that you know. I could do this. I could also decrease the ammonia. I could also decrease the temperature. So there's actually 4 different ways I could get this reaction to shift towards making more product. As long as I don't do it so much that I break the reaction by making it so that there's no more reactant or product left. All right, let's try the next practice question. Given the reaction at equilibrium, nitrogen gas reacts with oxygen gas to give you 2 moles of nitrous oxide or nitrogen monoxide. As the concentration of N2 is increased, the concentration of O2 will. Okay, this is a little bit annoying because of the way I pulled the question. It's not all written. I want to write it so that you can see it all in one line. Okay, that double arrow means you're at equilibrium. Okay, if I increase the amount of N2, right? So you know that the reaction will try and fix whatever you broke. So if you make it take too much N2, it's going to be like, I had enough N2. I'm going to try and put the amount of N2 I had before you came and messed with me. The only way to do that is to use it up by going forward in the reaction. If I need to use it up, I have to use up the other reactant and make more product. So that would mean that this is going to go down. This is going to increase because I'm going to make more of it to get rid of the extra N2. And the person I'm drawing this little squiggly bubble around is always the person who gets to go back to what they were doing before. So in this case, the concentration of oxygen will actually go down. All right, now back to our Haber-Bosch process. Given the equation representing the Haber-Bosch process, which change causes equilibrium to shift to the right? To the right would be forward. Okay, so before I start looking at answers, before I start looking at answers, I'm going to go through this one more time and make sure I know which are possibilities that would make me go forward. I'd have to increase my reactants, right? Because then they have to be used up. So that would force the reaction forward. Okay. So decreasing H2 is not going to be an option then. So I'd have to increase the concentration of N2. All right, once more, that Haber-Bosch process, they really like it. If only the concentration of N2 is increased. Now they want you to predict without telling you which thing they're going to talk about. If you increase this, this is going to go down. This will actually end up being constant at the end. This is going to go up, and temperature will actually increase. I'll have more heat energy produced. All right, N3 increases. That is true. NH3 remains the same. No, the only person who gets to remain the same is the person you actually touched. So it's the person you mess with that the equilibrium is going to try and get their world back to being exactly the way it was. Will the H2 increase? No, you're going to have to use it up to do the forward reaction. And H2 can't remain the same. Okay, now let's talk about energy one more time. Make sure that you understand how to show energy going in and out of reactions with chemical notation. A whole bunch of people did the homework from yesterday or from today. I'm making the video on Wednesday. And this homework is really for Thursday. Already wrote incorrect answers for how you write heat in a thermochemical equation. If you're writing a thermochemical equation, you show that it is endothermic or exothermic based on which side of the reaction you put it on. It's not the sign of delta H. It's not whether or not you make it positive or negative. Okay, because when you're writing something in a chemical reaction, it's always not going to have a sign on it. It's just going to be added to whichever side of the reaction it's going to be. So if it's negative, you're 100% right. It is exothermic. That's if I give you the number by itself. If I write it in the thermochemical equation, that's different. Okay, so there is a little bit of review here about things you should already know about a chemical reaction. You should already know what all your subscripts mean. You should already know what your coefficients mean. You should already know that a double arrow going backwards and forwards means it is a reversible reaction, which goes to equilibrium. And you should already know about how to use subscripts to make compounds and that you're not allowed to change them when you're balancing a reaction. Okay, now we're going to add to our knowledge of writing chemical equations by writing thermochemical equations, right? So, like next time your parents are like, I don't understand what's so hard about chemistry, and be like, fine, I have to go write thermochemical equations for 3 hours. And they'll be like, write a what now? It makes you sound really smart. Go with it. I would do that at parties if I were you. You know, if you want to look like a smart kid, just be like, I know. All day yesterday I was writing thermochemical equations. All right, so simply put, a thermochemical equation just shows the amount of heat in joules or kilojoules that is either given off or absorbed by the reaction. If it's endothermic, it will be going into the reaction on the reactant side. If it's exothermic, it will be coming out of the reaction on the product side. It will be produced by the reaction. So this is an endothermic reaction. So I am showing 58.1 kilojoules of energy going in on the reactant side. Okay, so that's an endothermic reaction. That has nothing to do necessarily with the sign I would put on this if I was just telling you what's the heat of the reaction for this or what's the change in enthalpy for this reaction. Okay, a negative sign does imply that you are giving off heat and that it is exothermic. And a positive sign does imply that it is endothermic, but you don't write those signs in a thermochemical equation. You just put it on the reactant side or the product side. Okay, so we don't write the signs. If it's on the reactant side, it's endothermic. If it's on the product side, it's exothermic. Okay, Now, what's great about this is you can already treat these like reactants or products, like I talked about earlier in one of the example questions. Okay, if temperature is lowered, you're taking heat out. And if temperature is raised, you are adding heat in. Okay, you're going to treat heat just like it's any other ingredient in the reaction. So let's do the practice questions. Given the equation representing a reaction at equilibrium, now where is the heat? The heat is on the reactant side. Okay, so that means I'm putting energy into this reaction. So this is an endothermic reaction. Okay, which change favors the reverse reaction? Well, this is a reactant. So if I want this to go backwards, if I want it to go backwards, I either have to, let me change colors because this one's hard to see. I could raise the product. If I increase the HI, the reaction will try to get rid of what I added. So it will go backwards. I could take this stuff away. If I take it away, it will try to replace it. So it'll force the reaction backwards. In terms of energy, if putting energy in makes this reaction go forward, I would have to take energy out to get it to go backwards. So I would have to I would have to cool it off. Okay, so that would be decreasing the temperature. All right, ammonia is produced commercially by the Haber reaction. Getting sick of the Haber reaction yet? Which change in temperature would favor the forward reaction? Let's talk about that. We talked about it already, but let's do it one more time. Heat is being produced by this reaction. It's on my product side. So this reaction is indeed exothermic. Okay, I'm producing heat. I would have to lower the temperature to get this to go forward. I'd have to, because if the reaction's already producing heat and you heat it up more, you're actually increasing the product. So you would force the reaction backwards. So you want to take heat away and force the reaction forwards. All right, now, what would be the result if I increase the temperature in this reaction? If that reaction doesn't look familiar to you, you'll notice that sometimes if you practice Regents questions really a lot, that they use the same reactions over and over again. All right, so H2 reacts with I2, so hydrogen gas reacts with iodine gas. You are heating this reaction up to get it to happen, so that heat, you're going to pretend it is a reactant. If it is a reactant and I add more reactant, the reaction should shift forward. So that's a shift to the right. So first thing I'm going to do is I'm going to make sure I understand that adding any reactant, including heat, will make this reaction shift forward. That's to the right, not to the left, right? Left, right? So I'm going to knock out the two answers that say shift to the left. If it shifts to the right, it will make more HI. So that's 3. If you shift to the right, you can't make less HI because you got to shift to the right makes more product. All right, given the reaction at equilibrium, the equilibrium point will shift to the right if you decrease the temperature. Okay, so you're going to want to practice these. Make sure you go back through if you need to rewind the video to the discussion. All right, one more video. This is the example that's used in the slideshow, N2O4. If you add 58.1 kilojoules of heat, this means it is an endothermic reaction. So if you increase the temperature, you're going to drive the reaction forward. So that means that you will increase the amount of NO2. So that's going to shift the reaction to the right, and the amount of NO2 will increase. All right, so we are all done. At this point, you're going to want to go to the Microsoft form. Actually, if you have not done the slideshow, make sure you go watch the videos in the slideshow before you do the Microsoft form, because I have questions in the Microsoft form about the videos. You need to make sure you really do the slideshow all the way through, particularly those video clips. If it's like just an interest one, like how they make soda, you don't have to watch it. But there were a couple I pointed out in the lecture just now. You really need to make sure you watch those.